Once again, the homework assignment for tonight is to take down the notes from this video. So, jumping right in, we've been talking about mean, standard deviation, and variance, and what that means. So, here's two situations. One is if a score was 10 away from the mean, but and a standard deviation of 2,000, it's relatively close to the mean. But if a score is 10 away from the mean with a standard deviation of 2, then it's very, very far away. The reason that would be is because the standard deviation is so huge with 2,000 that if it's less than 1 standard deviation away, much less, 10 is way smaller than 2,000 versus 10 when you had a standard deviation of 2 and 2 was the standard deviation. That means 10 would be 5 standard deviations away. That means that on those tails of the curve, of the bell curve that we're talking about, they're in the low percentages. So knowing the standard deviation alone does not tell you the whole story. You have to know where the mean is. You have to know how far away the standard deviation or the value of the score is from the mean. This is the reason why we start looking at standard deviation and converting the raw scores into standard scores. We're used to the middle score of the bell curve being the mean, and we're used to looking at the value away from the mean. Now we're looking at resetting that value, the mean, to 0, so that we can start looking at how many standard deviations it is away from the mean. We call that a z-score. And z-scores are very easy to compute. First, you have to have a value that you're talking about. You have to know what the mean is. So we used to use x bar. Another symbol that you're going to see here is another Greek letter. It's called mu. Mu is going to stand for the mean. It's going to be the average. So nothing different than what we're used to. And then sigma, as we learned in the last exercise, the last thing that we were doing was computing the standard deviation. So if you look at the two graphs, they look very similar. One is just setting the mean to a specific value of 0 so that we can now talk about, instead of the values, we can talk about how far away in standard deviations is that value. So here's an example. A summer camp is taking 220 sixth graders on a trip to an amusement park. Could be Disney, could be Universal, could be anywhere. For safety purposes, some of those rides have height requirements. The campers' heights have a mean of 56 inches and a standard deviation of 3. So if we're looking at our bell curve here, we're used to it looking like this. We're used to the 56 being in the middle, and then the first standard deviation being over here at 59, because that's 3 in the positive direction, and 53 being the other direction. And about 68% of our students in this field trip would be between those two values of 53 and 59. Well, now we're looking at not just the number of students, the percentage of students. Now we're looking at setting this to be 0 by finding the z-score. So that's the very first thing we want to do, is we want to say, okay, what is the z-score for a camper with a height of 62? 62 inches is our value. It's our x. 3 inches is our standard deviation. That's the sigma that we are used to. The mean of 56, that's mu. So in order to find the z-score, we would do x minus the mean of 56 and divided by the standard deviation. If I do that, I get 6 divided by 3 is 2. So anybody that is 62 inches is 2 standard deviations taller than the average person. So we would be over here at 62. So anybody that was higher would be higher than 62. Anybody would be lower, we're looking at that. So two standard deviations. Here's one standard deviation of 3. Here's the second standard deviation. Down here on our curve, this would be 1. This would be 2 instead of the numbers based off of 56. So that was it for that first example. Our second example kind of does a little bit backwards. It says the height of a certain student on the trip had a z-score, so they're giving us what it's equal to, and they want to know what the height is. So we're going to use the same information, except for we know z is going to be x minus mu, and there's our formula, divided by sigma. So z is what they're giving us, negative 0.5. Our standard deviation is still going to be 3 from over here. Our value is what we're looking for. Our mean is what we have still from that problem. So our mean is still 56. So we have everything except for one variable. So if I multiply both sides by 3, to get rid of the division problem on this side, I get negative 1.5 equals x minus 56. Division gets rid of multiplication, multiplication gets rid of division. I add 56 to both sides, and I get a value of 54.5 inches. So to answer the question, what is the student's height in inches if they are half a standard deviation below the average? Well, that's an inch and a half below the average in this case. Example 3, a certain ride requires riders to be at least 51 inches tall. The heights are normally distributed, so we're using that bell curve. Mean is still 56, standard deviation still 3. Approximately how many of the camp's 226 graders will not be allowed to ride the ride? So the table that I gave you in class will help us answer this. So we're still looking at a z-value. We need a z-value in order to answer this question. And then we're going to use that class of the table I gave you in class to do the rest. So the value is 51 inches. That's lower than the mean, so that has to mean that we're going to get a negative number because the mean is higher, and the standard deviation is 3. So our z-score is going to be negative 5 over 3, or negative 1.67. Now that negative 1.67, that's how many standard deviations below the mean we actually are. So if I look at the table that I gave you in class, there's 2 of them. One had negative numbers in this column here. One had positive numbers. We're looking at how many kids are below that negative 1.67. So if I come down here to negative 1.6 and go over to 0.7, wherever those intersect, that's the percentage of students below the 1.67 standard deviations. So we're looking at 4.75% of the 220 kids that would not be able to ride the ride. So if I go back here, 4.75, we said was 0.0745, there were 220 students. So when I multiply those out, that's about 10.5 students not being able to ride the ride. So maybe 10, maybe 11, somewhere around there. If another ride required the kids to be 60 inches tall, well, that's higher. That's higher than the average. There's going to be more kids that can't ride. Since it's higher than the average, there's more than 50%. We know that if we end up here with a number that was more than 50%, then that would give us some problems. But it says what percentage of students would be able to ride. So we got to be careful. It says not versus will. So we're looking at this chart again. We're finding the z-score. 60 was our value. Our average is 56. Our standard deviation is 3. We know that this is 4/3 or 1.33 repeating z-score wise. So the students that, thinking about this, the students that can ride, here's our average, was 56. And kids have to be at least 60 inches tall, which is 1.33 standard deviations away from that 56. The ones that can ride are the ones up here. Our table gives us the rest of it. Remember that there's 100% of data in here. So whatever we're going to get from our table that shades, I'm going to shade this in red, our table is going to give us this number. And if the whole thing is 100%, we're going to take 1 minus that red number, whatever we get from our table, and that's going to be how many students can ride the ride in here. So we got to look at the table. These are the negative numbers. We were on the positive numbers. 1. Oh, that's not the right one. We said 1. 133. So we're going to look at our table. 133. Here's 1, 3. Here's the other 3. Follow it down. Follow it across. Looks like 90.82% cannot ride the ride. So if 90.82% cannot ride the ride, that means that only 9% roughly can ride the ride. So here's what the answer should be. Find the percent of students who will be able to go on the ride that requires 51 inches or higher. So again, if we're looking at our average was 56. Here's where our value is at 51, somewhere over here. If we reset that so we can talk about standard deviations, we're resetting this to be 0, we have to find how many standard deviations this is away, which means we have to find a z-score. Well, the value is 51 minus the 56 divided by 3. That's 5/3, negative 5/3. So this is the negative table that we're looking at, negative 1.67. We'll go to the negative table, and that will give us how many kids are not able to ride, lower than 51. So this is negative 1.67. Well, we want to answer how many kids can. So again, if we know one side is a certain number, this is going to be from the table. We subtract from 1, and that will give us the answer to our question. Okay, so if we look at the table for negative 1.67, negative 1.67. Oh, we found that. That was the 4.75. We already found that number. So that was 0.0475. So what's the rest of the 100%? Well, that's 95.5 of our 6th graders that would be able to ride the ride. That's the percent. Are asking for a number of students, then I would have times that times the 220 that we would have. Okay, so now here's an application problem, a different application problem. No more rides. Families of students at Caliga High School were surveyed about their vacation expenses. The results were normally distributed. So we have a bell curve. The average was 2313. The standard deviation was 390. So the distance from here to our first one is 390, which would put us at 2703. And over here, technically, one standard deviation this way would be 2313 minus the 390. So 1923. So about 68% of our families at our high school would be able to afford a vacation between $1,923 and $2,703. And we want to know what is the percent of families that took vacations between $2,000 and $3,000. So we already know we're looking for kind of an in-between this time. So here's 2,000, here's 3,000. We're looking for this in here. Well, first, I would look at this and go, okay, if I knew this value, and I knew this yellow value here, from our table, we can figure out the black and we can figure out the yellow. So I'm going to go with the black first. The black would be 2,000 minus the average of 2313 divided by the standard deviation of 390. When I do that, I get negative 0.802. So for our table, it's going to be just 0.80. And for the yellow one, I'm going to get a standard, we wanted 3,000 minus 2313 over 390. And when I do that, I get 1.76. So I'm going to take the table values for 1.76 and negative 0.8, and I'm going to subtract that. So I get table values, negative 0.8 down here, negative 0.8 and 0 gives me 0.2119. 0.2119, and that's what I'm going to take away from the yellow. The yellow is a bigger range. So I got to look up 1.76. That's too far. 1.76 would be 1.76. Follow it down, follow it across. Looks like 9608. 0.9608 minus that. So 0.7489. About 75% of families in our high school could afford a vacation between $2,000 and $3,000, according to this problem. What percentage of families could do 1,000 to 2,000? This is where I'm going to stop this video, and you're going to practice. This is the hard problem. If you look at what we did here, you should be able to answer this question. Remember, here's the curve. The average was 2313. That's mu. The values now become 1,000 and 2,000. And we want to know what's the in-between. Use the table to find what the curve looks like here below 2,000, which is, you have to find its z value, and subtract off the curve when you find it at 1,000. And you have to find its z-score. When you subtract off those two, you should get that purple one in between.